In this video, I will demonstrate how to conduct an exploratory factor analysis using SPSS. And what we will use is the Holtz data from the Beginner's Guide to Structural Equation Modeling by Schumacher and Lomax. This data consists of 6 variables. 3 of those variables are measures of spatial or visual spatial skills, and 3 measures are measures of verbal skills. So we have visual perceptions, cubes, and Lanzens. Then we have paracomp, which is paragraph completion, sencomp, sentence completion, and word meaning. And so our goal here is to take this data set that had 301 individuals. I split it in half, and I took a random first half and a random sample and called it the second half. And so the goal here is that we'll go ahead and do a factor analysis, an exploratory factor analysis, to determine the factor structure of these 6 items. And we hypothesize that that those items will load on a visual spatial or a spatial factor. So visual perceptions, cubes, and Lanzens will load on a spatial trait, and then paragraph completion, sentence completion, and word meaning will load on a verbal trait. And so in order for us to then explore that and find out, we'll do a factor analysis. And if in fact we do find that we have this 2-factor structure, or whatever the number of factors end up being identified by the SPSS factor analysis program, we'll then take the second half of the data that I have saved in another spreadsheet, and then we'll do a confirmatory factor analysis on that as a way to validate results from the exploratory analysis in terms of how that sample factor structure will then be related to a estimated structure in the population. So to do the exploratory, we're going to go to Analyze, Dimension Reduction, and Factor. And then I'm going to click on the first variable and highlight them all, holding down the Shift key and moving them into the variables box. And then I'll click on Descriptives, and I want the correlation coefficients, the determinant, the KMO, and reproduced. I could obviously select more, but these are the main ones that I want to look at for this example. And then continue. And then for the extraction, I'm going to use a principal axis factoring because I want to be able to do a true exploratory factor analysis, not a principal component analysis. And then I'm going to click on Continue, and then I'm going to use a Varimax rotation because I don't want the factors to be related. I want them to be independent. And let me go back to rotation again. I want to make sure I click the loading plots. And then under Options, I want to sort the factor loadings by size because it makes it easier to identify which variables load on which factors. So then I'm going to click on OK. So now for this part of my report, I have the output. I have the correlation matrix, which gives all the Pearson correlations between the pairs of variables that are in this data set. The determinant, 0.129, that value is acceptable. We want values above 0.0001. And the reason we want values above that is because what that signifies is that if we have values above 0.0001, then the correlation matrix can be inverted and the factor analysis can proceed. Our KMO is above zero point 0.5, so we want that to be above zero point 0.5, and we want our Bartlett's test to be significant. So what this is telling us is that we don't have a lot of multicollinearity within our correlation matrix. I'm going to come back to the communalities in a minute, but I want to go down to this total variance explained. What this tells us is that we've identified two factors that have eigenvalues above 1. And those two factors, if we come over here, are explaining the first factor, a little over 35% of the variability in the data structure, the data matrix, and the second factor is identifying almost 20%. Both factors together are identifying over 55% of the variability in the 6 variables that were analyzed. Now let's go down to the factor matrix. So this matrix tells us what our factor loadings are. And in this case, our factor loadings, they're not as interpretable as they could be if we rotate that matrix, and that's why we asked to get the matrix rotated or have it rotated. And so you could see that these factor loadings for visual perception are not that much different, and we could say the same thing for cubes. These should have a standardized loading of 0.200 really difference in order for them to be uniquely identified as being on one factor. So I want to go down here, and by rotating that matrix, we can see that it's much more interpretable. It's very clear that sentence completion, paragraph completion, word meaning, and the 3 visual spatial tasks are loading on separate factors. And if we come down here, we can see that for this first factor, you can see how close those variables are to that line or vector that represents factor 1. And for factor 2, you could see how close to this vector that these 3 variables, how close they are to that line. So you can imagine if these axes were moved this way, they would be further apart or further from the variables that they're representing. And so these axes are rotated so that they're closer to the variables, and thus making it much more interpretable in terms of which variables are loading on which factors. The other part that I want to point out is that we have these reproduced correlations. So what happens is that the factor analysis estimates the correlations based on the data matrix. And the residual is the difference between the actual correlations and the estimated correlations. So if you go up here, you can actually see what the real correlations are from the, the observed correlations are from the data that was analyzed as compared to the estimated correlations. And so you can see our estimated correlations, there's very little difference between the observed and our estimated based on our model. Now let's go back up to the communalities. So how do we interpret these communalities? If I look at my factor loadings, what this means is, for example, like the square of this plus the square of this. So the square of 0.91 basically plus the square of 0.34 is let's see, I got to make sure I'm on the right one here. Sentence completion. So if I add those squared values up, this will give me my communality. So what it's saying is that the model, that the two-factor model is explaining about 83% of the variability in sentence completion scores. And that's good because we want our communalities to be 1 or above. Cubes is a little low, so if we go down here and look at cubes, we can see that if I square this value 0.80 plus the square of this value, it's going to give me about 0.95. So 59, I'm sorry, I got the wrong one again. Cubes, it's going to give me about 16.9 or about 17%. That two-factor model is going to explain about 17% of cubes. So you can see that relationship. It'd be nicer if these matrices or these tables were a little closer together. But nevertheless, now we've identified, based on our rotated factor matrix, we've identified a verbal factor and a spatial or abstract reasoning factor. And so now what we want to do is take that factor, that two-factor solution, and we want to relate these items to factor 1, the verbal factor, and factor 2, the spatial factor, in a confirmatory factor analysis to further validate the this factor structure as it would be hypothesized to exist in the population.